Hello, students, and welcome to this absolute masterclass. Today, we are tackling a super high-yield topic for your UPSC preparation, tropical cyclones. We are going to cover literally everything you need to know, from the ground up, all the way to advanced climate dynamics. By the end of this session, you won't need to look at another resource. So let's get right into it. Here is our roadmap for today. We will start with introduction and basics, move into the necessary conditions, break down the cyclone engine, look at structure and classes, trace their movement and landfall, and finally discuss climate change impacts. All right, Section 1. Let's build that foundation with introduction and basics. So where do these massive storms actually form? Well, they have strict locational limits. They only form over warm water bodies, specifically between the 10-degree and 30-degree latitudes in both the northern and southern hemispheres. But here is the really interesting part. They never ever form right at the equator, between 0 and 10 degrees. Stick a pin in that, because I'm going to tell you exactly why in just a minute. Now pay close attention here, because this is a classic prelims trap: the naming conventions. The physical storm is exactly the same everywhere, but the names change depending on where you are in the world. In the North Atlantic and Eastern Pacific, they call them hurricanes. Over in the Northwest Pacific, they are typhoons. And in our neck of the woods, the Indian Ocean and South Pacific, we just call them cyclones. Same exact monster, just different names. Moving on to Section 2, necessary conditions for formation. Think of a cyclone like baking a cake. You need a very specific recipe. There are 3 essential ingredients. First, your sea surface temperature, or SST, has to be warm, strictly above 26.5 or 27 degrees Celsius. Second, you absolutely need the Coriolis force to create that spinning motion. And third, low vertical wind shear. Why low? Well, because if the wind speeds are consistent at different heights, those storm clouds can grow straight up, vertically, without their tops getting completely sheared off by intense crosswinds. Let's quickly talk about that second ingredient, the Coriolis force. It is basically an apparent force caused by the Earth spinning on its axis, and it deflects winds to the right in the northern hemisphere and left in the southern hemisphere. This is exactly what gives the storm its spin. And remember earlier when I said cyclones don't form at the equator? Here is your answer. The Coriolis force is essentially 0 at the equator. No Coriolis, no spin, no cyclone. Simple as that. All right, Section 3. The cyclone engine and its mechanism of power. To really understand this engine, you have to know what fuels it, and that is the latent heat of condensation. Let's break down the physics real quick. Evaporation cools things down, right? But when that water vapor rises up and turns back into liquid water, which we call condensation, it actually releases heat into the surrounding air. That released heat acts as the primary fuel source for a tropical cyclone. And this creates a massive positive feedback loop, known as the wishy theory. Here is exactly how it happens. First, a small disturbance creates a low-pressure area over that warm ocean water. Warm, moist air rushes in, rises, and then cools, causing condensation. That condensation releases latent heat, which warms the air around it. Since warm air is lighter, the air pressure drops even more. This severe drop in pressure acts like a giant vacuum, sucking in even more wind. It's a continuous, crazy engine that takes a tiny little disturbance and turns it into a total monster of a storm. Next up, Section 4. Let's look at the structure and classes, basically the anatomy of the storm. Right smack in the middle of a cyclone, you have the eye. Because the air is actually sinking down in this exact spot, the eye is notoriously calm and clear. But right outside that peaceful center is the eye wall. And wow, what a contrast. The eye wall is where you are going to find the most violent thunderstorms, the absolute heaviest rain, and the strongest, most destructive winds in the entire system. For your exams, you are definitely going to want to memorize this IMD classification table. A tropical disturbance is just low and variable. Once it hits up to 63 kilometers per hour, it escalates to a depression. Between 63 and 118, it's a tropical storm. But the moment those sustained winds cross 119 kilometers per hour, boom, it is officially a hurricane or a severe cyclone. And just keep in mind, extreme events like the tragic 1999 Odisha supercyclone blew way past these top wind speeds. Section 5. Movement and landfall. Let's track these storms. These massive systems are constantly on the move. Driven by the easterly trade winds, cyclones will generally travel from east to west. But at the same time, a fascinating phenomenon known as beta drift causes them to slowly curve poleward, pushing them toward the mid-latitudes. So let me ask you a quick question to test your concepts. Does a cyclone always die immediately the second it makes landfall? Well, the general rule of thumb is yes. Once it crosses over land, it gets totally cut off from its warm ocean fuel source, and usually just fizzles out in about 2 to 3 days. But, and here is a fantastic high-value point for your main's enrichment, let me introduce you to the brown ocean effect. This is a rare phenomenon where land that is super saturated and highly humid basically acts just like the ocean. It provides enough moisture from the wet, flooded soil to keep a cyclone alive or even re-intensify it far inland. A textbook example was Tropical Storm Bill back in 2015, which totally surprised forecasters by re-intensifying over flooded soils in Texas. Finally, Section 6, climate change impacts on these extreme systems. You can absolutely expect questions on this. The extra heat we are pumping into the climate system is completely changing the game for cyclones. Warmer oceans are basically high-octane fuel, causing storms to intensify much more rapidly. On top of that, a warmer atmosphere physically holds more water vapor, meaning much heavier, catastrophic rainfall. Storms are also moving slower over land now, drastically increasing our flood exposure. And up in the north, Arctic warming is actually shifting hurricane tracks further to the west. Just look at this shocking real-world example. Hurricane Milton in 2024. Fueled by insanely warm 30 degrees Celsius waters in the Gulf of Mexico, this storm went from a basic tropical storm to a catastrophic Category 5 hurricane in just 24 hours. That is rapid intensification, and it's a terrifying reality of climate change. When these storms make landfall, please remember this critical point. Water, not wind, is the deadliest factor. The biggest hazard is storm surge, that is ocean water physically being pushed inland by the wind, sometimes piling up to 20 feet high. Combine that with extreme inland flooding and landslides from the torrential rain, plus destructive winds that can even spawn tornadoes. Seriously, storm surge and flooding accounted for roughly 3/4 of the deaths in historical storms like Hurricane Katrina. I want to leave you with an analytical thought, especially for your disaster management prep. With our oceans warming at this unprecedented rate, how do we need to completely redesign our coastal infrastructure and early warning systems to survive tomorrow's supercyclones? It is a big question. Keep studying, keep revising this masterclass, and keep that question in mind as you prepare. Thanks for joining me today, and I'll see you in the next session.